This is our video lab report on Energy and Force by Beth Feldman, Alex Haver, and Isabella Olet. We're Group 1B.
In our experiment, we addressed the question, how is the force exerted on a car during a crash changed when it crashes into a hard surface versus a soft surface? We hypothesized that the car that collides with a softer surface will have a smaller force exerted on it due to energy being absorbed by the surface and will result in an extreme change in velocity after the crash. The rate that the car is moving was kept constant along with the distance away from the wall, but the force of impact was changed. We used iLab software to determine the force and velocity of the car during the two different crashes. Our results are listed below.
On this slide, we're going to talk about our system schema and our free body diagram. So the three objects in our system, it's going to be the earth, the car, and the wall. So the earth against the wall, there's going to be contact and gravitational force on that. The car and the wall, there's going to be contact force once it hits. And then the car and the earth is going to have contact and gravity force because it is in contact with it, and there is gravity keeping it on the ground. Our free body force diagram, there is a resistive force from the air in the car. There is a frictional force from the ground to the car. There's a force applied from the hand to the car, and there is gravitational force from the earth onto the car. So this force diagram shows the forces acting on the car before the impact with the wall, and then after the impact, there would be a force of the wall acting back on the car in the opposite direction of the initial motion.
We also looked at the different compliancies of surfaces. Compliancy is defined as the property that a material has to undergo an elastic deformation when an applied force is acted upon it, and is also known as the stiffness of a material. When investigating force and energy, force can be defined as an interaction between two objects that both exert some sort of force on each other. Energy can be defined as the ability for something to do work, and it can be transformed and exist in many different forms. Work is defined as a measure of energy transfer that occurs over a certain distance.
On this slide, we're going to talk about the models that we used to reason through our experiment. So the first image shows the force that the wall exerts back in the car after the impact. So that's going to show kind of the spring concept on that first image. And then the second image is just a diagram that shows the physics behind how airbags actually work. It's going to represent how the spring could be modeled kind of like an airbag. And this just talks about how airbags reduce the force of impact by reducing the distance the body travels, which prevents it from reaching a higher velocity during the crash.
In order to conduct our experiment, we needed a meter stick, a wall, a thin pillow, iLab and iLab software, and a laptop. We conducted the experiment by pushing the iLab into a wall and then into the wall with a thin pillow in front of it. For each trial, the iLab was started 1 meter away from the wall. We recorded the force of the impact and the velocities that the car was moving after impact. The average velocity of the cars was found using iLab software from the two trials. Velocity time graphs and force time graphs were compared to see how the force exerted on the different surfaces affected the velocity of the car after the crash. We also looked to see how data could qualitatively transfer to explain how airbags work to reduce the force of impact in a car crash.
So our final results, in general, we figured out that the car that crashed into the bare wall had an average force of over 15 newtons exerted on it. The car that crashed into the pillow against the wall had an average force of less than 2 newtons exerted on it. So therefore, we concluded that the car that crashed into the more compliant surface had a smaller force that was exerted back in the car and the passenger after the crash, and it had a less extreme change in velocity backwards because of the energy absorbed from the surface. So in a real car crash, this can translate into the airbags cushioning the passenger for a more safe impact.
Here we have the results from the car hitting the wall. As you can see, there is a very strong force that is acted on the car after the impact. You can also see that the change in velocity is not very great from the car hitting the wall. Here we have the results from the car hitting the pillow. As you can see, the force that is acted on the car after the crash from the pillow is not very strong. You can also see that the change in velocity here is much greater than the change in velocity from the car hitting the wall. You can see that the car is moving at a much higher velocity prior to the crash than it is after the crash.
We confirmed our hypothesis that the car that crashed into the softer surface had a much lower force applied to it during the impact than the car that hit the wall. The variable that we changed and measured was the surface that the car crashed into, which in this case was the wall and the pillow. This showed the difference in compliancy of the two objects.
Higher velocity post-impact was seen when the car hit the wall, which was a much firmer object that did not absorb much energy. The trial with the car crashing into a soft object best shows the effectiveness of airbags. Possible human errors must be taken into account when reviewing this data. Thanks for watching!